What's up, guys? Welcome to this R session. For today, we're just going to analyze a very simple first passage time problem. As always, if you're not too familiar with R, maybe the things you want to brush up on are maybe calculating loops, matrix multiplication, and drawing plots. It's nothing too heavy we're going to cover today, but maybe you want to brush up on that. Other than that, I would just suggest maybe going over the theory again of how to calculate transitional densities for Markov chains. And then also make sure you're familiar with the theory around first passage time problems for Markov chains. And yeah, that's that. So let's jump in. Cool. So let's have a look at the template file I've given you. Okay, so right, we've got one goal today, and that is to analyze first passage from state 1 to state 2 for a Markov chain with transition probability matrix given by a simple 2x2 matrix where we have the probability of moving from state 1 to state 1 in one step is going to be 0.9, 1 to 2 steps in one step, 1 to 2 in one step is going to be 0.1, 2 to 2 in 1, 0.7, 2 to 1 in one step is going to be 0.3. Okay, so nice and simple chain. And then I give you a bunch of tasks in order to do this. First task, calculate and record gamma 1 to k and gamma 2 to k for k running from 0, 1, 2 all the way to k max, and you can choose whatever k max is. Okay, and then I give you some subtasks there just to help you along. Okay, then task 2. Evaluate the recursive relation for f1 to k. Okay, so this is where we're going to evaluate the first passage probabilities for k running from 1 to all the way up to k max using the probabilities calculated in task 1. Okay, and we'll look at that in a second again. And then I want you to plot the resulting distribution. Again, I'll give you some variables that you can populate. And then finally, task 3. Compare this to the geometric 0.1 distribution. Okay, so I give you the parameter there. You may use the geometric, so that's just a function from R, built-in function you can use. And then I want you to approximate the mean and variance using the probabilities from the recursive relation, so that's from task 2, and then comment on the results. Okay, so we're going to compare presumably the exact distribution to our one we calculated, and we're also going to calculate some moments and compare that to the true moments to see what our numerical procedure produces. Okay, so I guess before we start, we maybe just want to refresh ourselves on how to calculate first passage time probabilities algorithmically, because that's essentially what we're going to be doing here. I'm going to ask you to calculate the transition probabilities, and then, well, the idea behind that is to help you in order to calculate the first passage time probabilities numerically. Okay, so let's have a look at that. Okay, so recall that the expression that relates transition to first passage, or return for that matter, follows from decomposing the transition probability. Okay, so take the probability of transition from state I to state j in k steps, and we just decompose that as the probability of first passage from state I to state j in, say, r steps, multiplied by the probability of moving from state j back to state j in the remaining k minus r steps, where r notionally means here some interim time point at which first passage could have occurred. And then we obviously have to account for all those possible points at which first passage could have occurred by summing all those product probabilities up, running from 0 all the way to k. Okay, so that's just a decomposition of the transition probability in such a way that we can relate it to the first passage time probabilities. Okay. And this expression holds for all k running from 1, 2, etc., subject to the initial condition that the probability of first passage in 0 steps is going to be 0. Okay, so we impose that little boundary condition. Okay, so again, why is this useful? As I would have shown you in the lecture, well, we can find an explicit expression by expanding this sum and rearranging the terms, right? So what are we looking for in this case? Well, we're looking for the first passage probabilities. We have an expression for the transition probabilities. Okay, so what do we do? Well, we want to write an explicit expression for the first passage probabilities, and that's essentially what we're doing. Okay, so first thing we do, well, we take that summation, we expand it by taking out the last term, essentially. And we note that that last term is just going to be the probability of first passage from state I to state j in k steps multiplied by the probability of moving from state j to state j in 0 steps. Okay, and that little probability is going to be 1. So we can actually isolate that first passage time probability Fijk, right? Now, just rearranging that expression, we find the explicit expression for the first passage probability that we're looking for. And now it's also obvious why we're sort of calculating the transition probabilities first, right? So if we calculate the transition probabilities, we have almost all the terms on the right-hand side of that equation, right? So the first one that features there is the probability of transitioning from state I to state j in k steps. The second one that features there is the probability of moving from state j to j in k minus r steps. Okay. Now we're going to evaluate this equation for k running from 1, 2, 3, etc. all the way. So, well, we just need all the transition probabilities for k running from 1, 2, 3, etc. We're actually going to need from 0, but we'll get to that in a second. But we're also going to need that for the transition probabilities from moving from state j to state j. Okay, and how do we know that? Well, we can just look at what that index looks like. Right, so yeah, I guess that's the other note I put here. Note that the index r, so that's in the summation, runs from 0, 1, 2, now all the way up to k minus 1 because we've taken out the last term. Okay, so those are actual time points to which the index corresponds to, which will be important for how we calculate this in R, because R starts indexing from 1. But in any case, we'll get to that in a sec. But then we also note that the index k minus r goes k, k minus 1, k minus 2, etc., 2, and then 1. So the endpoints there are sort of important for what we're going to try and do. Okay, so have to evaluate the transition probabilities. Well, how are we going to evaluate this expression if we don't have the first passage probabilities? Okay, well, that's taken care of by the fact that this is a triangular expression, remember? So we're going to start with k, 1, 2, 3, etc., and then we're going to sort of recursively populate those elements. So we'll actually have all the elements on the right-hand side of that equation. Okay, so let's go back to the code. Right, so let's look at task 1. Calculate and record gamma 1, 2k and gamma 2, 2k for k running from 0, 1, 2, etc. up to k max, and you can chase k max. Okay, so I'm just going to choose k max as 10 for now. Okay, and then we're going to calculate and record the transition probabilities. How are we going to do that? Well, we're going to use our updating equation for the marginal distributions. We're going to exploit that, try and calculate transition probabilities. How do we do that? Well, we just pick our initial distribution in the appropriate way. And remember from our previous little R session, how do we do that? Well, if we set the initial distribution, for example, that, well, state 1 is occupied with certainty, and this is two-state chain, so we'll just set that distribution to 1, 0. Well, then our updating equation will actually return what? It'll return all of the transition probabilities starting from state 1. Okay, so when we update that equation, we just read off the second element to get gamma 1, 2. Simple as that. Okay, so that's the initial distribution for gamma 1, 2. Well, we need another initial distribution for gamma 2, 2. So we just call that D2, and well, we say that, well, because we're starting from state 2 needs to be occupied with certainty at time point 0. Okay. And then I give you two vectors, which we're just going to use as storage. So we're just going to repeat NA a number of times. Okay, so you're just going to create some storage vector. So repeat NA and repeat it Kmax plus 1 times. Okay, and do the same for gamma 2, 2. Okay, so why do I have Kmax plus 1? Okay, so note here that the task says calculate these probabilities for k running from 0, 1, 2, all the way up to Kmax. So how many elements are there? Well, it's Kmax plus 1 because we are including 0 there. Okay, so the first element in this vector is actually going to correspond to k equals 0. Okay, so the time index 0. So that's the offset I'm talking about, or what I was talking about earlier. Okay. And well, because we're evaluating from naught, we need to plug in the boundary conditions for, or the initial conditions, I guess, for these transition probabilities. And those are, well, that the first element in this vector, which corresponds to transition in 0 steps, okay, is going to be what? So probability of transitioning from state 1 to state 2 in 0 steps, well, we define that as being 0, right? Also, for gamma 2, we say that, well, the probability of transitioning from state 2 to state 2 in 0 steps, so the first element there corresponding to time with 0, well, that's just going to be 1 because it's already there. Okay, so that fixes the initial element in that vector. Now we need to populate the other elements in that vector by way of our little updating equation for the transition probabilities. And how do we do that? Simple for loop. Okay, so let's say for k, why do I say equal again? K in 1 to k max. K max. Do the following. Okay, what does our updating equation look like? It's typically what delta k transpose equals delta k minus 1 transpose post multiplied by gamma. Okay, so we're going to say that, okay, update d1, so the first distribution. How are you going to do that? Well, take the transpose of d1 post multiplied by gamma. And then we're going to have to transpose that again because we want to store a column vector all the time. Okay. Then we want to do the same thing for D2. Okay, so that's just going to update the marginal distribution. Now, because we've picked the initial distributions in a particular way, we can actually read off the transition probabilities at each iteration for the corresponding time index. Okay, now note here, time is going to go from 1 to all the way to k max. Okay, but the points at which we store that are 1 up from that. So, well, we're going to have to store gamma 1, 2. So let's just borrow it from there. And we're going to store its k plus 1th element as what? Well, we read off the second element in that updated distribution vector. Okay. Cool, and we do the same for gamma 2, 2. Read off the second element there, and that'll give us the transition probability. Okay, at time k. Cool, and that's going to be that. Maybe what we'll do is we just want to check that our calculation worked, so we can quickly plot these. So let's go plot gamma 1, 2, and well, we're going to make it as a function of time. Talk about what time is in a sec. Okay, let's just plot it. We need to define the time vector. What does time look like? Time runs from 0 all the way up to k max, right? So that's what time looks like. Okay, so let's run this calculation. We already have gamma, etc. Okay, perfect. Let's run this plot, see what happens. Okay, cool. So that's what our transition probabilities look like at the relevant time indices. So note again here that we've started from 0 here, and we've evaluated up to k max, which we've set to be 10. Okay, let's check 2, 2. That looks like, okay, starts out at 1.7. Yes, okay, so that makes sense. Right, so that gives us the transition probabilities. I guess we can now move on to calculating the recursive relation. Okay, so task 2. Evaluate the recursive relation for f1 to k, for k running from 1 to all the way up to k max. Note again, we start here now at 1. Using the probabilities calculated in task 1, okay, we're happy with those, and then we want to plot the resulting distribution. Okay, and then I'll give you f1, 2 there. Okay, so we need to create a vector of storage again, so just repeat a bunch of NAs again. Again, we're going to have to repeat them in k max plus 1 times. Okay, why do we do that? Well, we're going to have to initialize this vector, or at least if its first element, as being what? Well, the first element has to be 0, meaning that, well, probability of first passage from state 1 to state 2 in 0 steps, oh, right, so 0 corresponds to the first index in R, has to be 0. Okay, then we're going to have to populate the other elements by evaluating our recursive relation. Okay, so what is our recursive relation look? So you can just have a look at your notes again. So let's run k again. So k for k in 1 to k max. Do the following calculation, right? And what does our calculation look like? Okay, so, well, f12 at k plus 1. So remember, k corresponds to time here, but the index in the vector is 1 up from that. So that's where we store that. So f12 k plus 1 is just going to be equal to what? Well, it's going to be gamma 1, 2, k plus 1 minus what? We've got some summation, right? So the probability of transitioning from state 1 to state 2 in k steps minus the sum of what? The probability of first passage from state 1 to state 2 in how many steps? Well, r steps. Okay, so there's going to be an index there, multiplied by what? The probability of transitioning from state 2 back to state 2 in the remaining number of steps. So there's going to be another index there. Okay, so there are lots of elements in this sum potentially, and this outer loop is essentially looping through that equation. Okay, through the updating equation. Okay, so what does that index look like? Well, the index for the sum runs from what? R running from 0 to k minus 1. Okay, so that's the time to which it corresponds. Okay, now remember our index for the vector in R is 1 up from that, so that's going to be running from 1 to k. Okay, that's cool. So that's the index for the first element in that summation, or I guess the first element there. And then we need the index for the second element. How does that go? So that goes k minus 1, k minus 2, all the way down to 2, and then 1. Okay, so, well, what does that correspond to? Well, we can just reverse that index that we just had. Okay, so k running from k to 1, and then we add 1 to that. Just shift it up 1, so that it runs from the corresponding time index runs from k minus 1, etc., all the way down to 1. Okay, so just I guess to see that, maybe let's run, we've got a time vector, right? So let's go time running from 1 to k max, right? Okay, so what is the first element in that vector all the way up to k max? Okay, what does that look like? Okay, it goes 0, 1, 2, 3, 4, all the way up to 9. Okay, so you can see with the time index to which that corresponds. Okay, so if maybe we're at the last element in the summation, that index runs from 1 to k max. Well, what does that look like? 0, 1, 2, all the way up to 9. Okay, that makes sense. What does the reverse of that look like? So k max running down all the way to 1. Well, that's just going to be 9, 8, 7, 6, 5, all the way to 0. Okay, but look at the endpoints there. If k here is at k max, those are not the correct indices, time indices, so we need to add 1. So it goes 10, 9, 8, 7, all the way down to 1. Okay, cool. So that's our recursive relation. The task says plot the resulting distribution. Sorry about that. Okay, plot f12 as a function of time. Type of plot I'm going to draw one with little bars. So type equals h. Color, we're going to make it light blue. And then we're going to say, line width, we're going to make 3. Okay, just so it pops up nicely. Okay, so let's run all of it. Okay, cool. And it plots our distribution. And what do we get out? We get a nice skewed distribution. We see that the probability of first passage in 0 steps, that's going to be 0. Probability of first passage from state 1 to state 2 in 1 step, that's 0.1. Does that make sense? Well, we look at our transition matrix. Yes, that makes sense. Perfect. Next thing, okay, so we will have to calculate the other ones in a different way. But anyway, let's maybe look at this distribution. Okay, one thing we can do is, well, we picked Kmax as 10, right? So we can only sort of see the first bit of that distribution. So let's maybe just make Kmax bigger. So we're going to widen our time index set, and then we're going to get a better idea of the shape of the distribution. Okay, so I'm going to go and I'm going to say set Kmax equal to 50. Okay, so let's plot that distribution. There we go. Cool. So nice skewed discrete distribution. Excellent. Okay, so I guess that's that for task 2. Okay, so we've calculated the first passage time distribution numerically. So we have, 51 odd probabilities to work with here. But then task 3 asks us to compare this to the geometric 0.1 distribution. You may use the geometric and then approximate. Okay, so first thing we want to do is just type question mark the geom, and then look at what the help file says for that. Okay, so the geometric distribution, description, density distribution function, quantile function, blah, 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 for the geometric distribution. Okay, and then we have that it has a bunch of parameters. So dgm is parameters x, which is just the vector of quantiles, or representing the number of failures in a sequence of Bernoulli trials before success occurs. What is prob? Probability of success in each trial. Okay, cool. And then log, that's just another parameter. Okay, and then we have details. The geometric distribution with prob p has the following density. So they give an expression for it there, etc. Okay, so let's compare that. We've got a plot, so let's plot the geometric distribution over the same time index for that parameter. Okay, so we're going to go, I'm going to draw lines. Now, strictly speaking, it doesn't make sense to draw lines. This is not a continuous distribution, but I guess it's just going to demonstrate it properly. So bear with me. Okay, so we're going to evaluate the geometric distribution at all of the time points that we had there. We're going to set the parameter probability of success 0.1. And we're going to plot this as a function of time, obviously. And let's make it purple. Okay, so let's see what happens. Oh, no. So what went wrong? Doesn't look the same, right? So we must have made a numerical error, right? Or did we? Okay. Right, so maybe we don't know. Okay, so let's maybe check ourselves here. Okay, so we've got the geometric distribution, and well, let's maybe go to an analytical analysis of this. Let's maybe go back to our notes. How would we analyze this problem analytically? Well, one way to do that is by way of generating functions, right? Okay, so we go back to our theory. How do we do this? Again, okay, well, we need to find a generating function for first passage from state 1 to state 2. How do we do that? Well, we need pseudo-generating functions because we've got an identity for that the generating function we're looking for in terms of pseudo-generating functions. Okay, so how do we find the pseudo-generating functions? We have an explicit expression for that. Okay, so let's do it that way. So, yeah, let's evaluate the matrix of pseudo-generating functions first. Just take the identity matrix minus s times gamma, invert that expression, and then, okay, well, what do we get? A bunch of ratios of polynomials, and then we say, okay, well, we want the generating function for first passage from state 1 to state 2. Okay, we're going to have to read off the appropriate elements from that matrix. plug it into that expression, which we do. We end up again with a nice simple expression. We find that it's 0.1s divided by 1 minus 0.9s. And then, like we said, by the uniqueness of the probability generating function, we recognize this as geometric alpha, where alpha is just a distribution of this, the parameter of the distribution, and we need to identify the appropriate parameter, which we've done. Okay, so, well, why is our thing not matching up? Well, as it happens, there are actually two variants of the geometric distribution, and this is where you need to be careful. So the first variant is the one we've just derived here, and it has support on 1, 2, 3, etc. Okay, so the other, its generating function looks slightly different, but it has support running from 0, 1, 2, 3. So the difference there is where it starts running from its support. Okay, now, so we've analytically identified the correct one as the one with support running from 1, 2, 3, etc. Okay, now practically these two differ only in where they start actually assigning positive probability. So the probabilities are actually the same, they just shifted in the domain. But their interpretation is actually different. So you can go check yourself why that is. A little bit of homework for you. But in any case, what that means for our little problem here is, well, how do we fix this? Okay, so there are actually two ways to fix this. One is just to calculate the zero truncated distribution. Why do I say that? Well, it's because if you look in the help file again, you'll see that the geometric distribution in R that they use is the one with support 0, 1, 2, etc. Okay, so we've actually used the wrong one. Right, but easy fix. We can either do the zero truncated one. You guys should know from Stats 2 or basic probability theory how to truncate a distribution. But alternatively, in this case, you can just shift the time index because those probabilities are the same. So we shift the time index, evaluate it as that, and then let's see what that produces. And then finally we have that our probabilities line up. Okay, so our numerical calculation was not incorrect. It's actually perfectly fine. Okay, so do we conclude then that our numerical approximation is good enough for rock and roll? Well, it looks like it. I mean, we can evaluate it rather easily. It seems to match up with the theoretical results, so can we trust this? Well, it depends on what we want to do, right? And this is why task 3 actually asks you to approximate the mean and the variance using the probabilities from the recursive relation. So not the true one, not the true distribution, but the recursive relation. And then comment on the results. Okay, so I'm going to ask you to calculate the mean. Okay, so if I give you a sequence of probabilities corresponding to the outcomes of a random variable, how do you calculate the mean? Okay, well, that's nice and simple. We just go, well, sum up events times their probabilities, F1, 2, okay, and that'll estimate the mean for us. Okay, so let's look at what mu is. Oh, sorry, that's not going to work. Okay, so go there. Mu. Okay, and what do we find? Okay, we find that the mean is 9.690773. Okay, so that doesn't look good. Why? Because we know the true result is going to be 1 divided by 0.1. We know that from the geometric distribution, or we just go read it up. Okay, so that's not good, but maybe let's look at the variance. How do we calculate the variance? Well, once we've calculated the mean or estimated the mean, well, we can just say whatever the outcomes are minus the mean squared multiplied by the probabilities and then sum them up. Okay, so let's calculate those two, and then we see that the variance is 76.58. Okay, now again, if we can just go plug in the true parameter in the true distribution, we're going to check what the true answer is. We'll find that the true answer for the variance is actually 90, so we're pretty far out. It's not doing well. Right, so how do we fix this? well, we're pretty confident in our numerical approximation. It seems to be working well. But maybe one thing we didn't do, and this is something I warned you about, was maybe we didn't pick K-max high enough, right? So let's change K-max to 100 this time around. Okay, and indeed, what do we see? Okay, we only have to evaluate that tail pretty far. Okay, so we incur a bit of computation time, but it seems like we are closer to the true answers, which are 10 and 90. Okay, so Muse is 9.99, 89.7. Okay, cool. So maybe that's not good enough. Let's try 150. Rerun the analysis. Okay, it's starting to look a little bit better. 200. Okay, so at 200 we get a mean of 10. Okay, that's the true answer. Sure. Okay, we have to evaluate pretty far. Look at those probabilities. They can become pretty tiny, but they do add up. Okay, so and our mean is 10. Because now our mean is correct. Well, that mean features in the actual calculation for the variance. So what's going on there? Okay, so it's still not good enough. So maybe how far do we have to go? Let's try 250. And there we have it. Okay, cool. Right, so we're happy with our numerical calculation. We see that it's correct. It compares well to the true distribution. One thing we do note though is that we have to calculate that recursive relation pretty damn far before we actually get any accuracy when we want to estimate things like the mean and the variance. And those are only the first two moments. Right, now I guess you guys should already know this by this point, but if you don't, as it happens, these sort of errors become worse just because, or these errors become worse as you go up the order of the moments that you're trying to calculate. And maybe also with the complexity of the statistics you're trying to calculate. So again, that just sort of emphasizes the point that you have to be really careful in how you actually pick K-max there when you do calculations numerically. Okay. So I guess that's that for what I wanted to do today. I'll leave up a nice homework problem for you to check out. I hope you found that interesting, and then I'll see you in the next one.